The opposite of esterification that we just saw in the last the slide before last is ester hydrolysis. It's starting with the ester and reacting it with water to create the corresponding acid and alcohol. So it literally is the reverse. And when you create esters, those are reversible equilibrium reactions, which means in principle you can start with the ester and encourage the reaction to kind of go in reverse. So you can see on this slide I've again kind of color-coded the water molecule to show you where the atoms end up. Whereas we tend to use acids to create the esters, these are promoted by using bases like hydroxide, and that's again a very common reaction, just as making the esters in the first place. Not only common in the lab, but common in natural reactions that occur. So here are, I believe, the esters on that previous slide, and we're talking about them, showing them rather undergoing hydrolysis. That word, by the way, the hydro means water, lysis is the suffix that means to cut, or in this case to break a chemical bond. And so when you use water to break bonds, in this case to chop up an ester, that is termed hydrolysis. So just as you want to be able to know what ester you can make from a given acid and alcohol, you want to know how to do reactions like this as well to show how hydrolysis works. There's lots and lots of esters that are of interest. Fatty acids and fatty esters are very common in our bodies. They oftentimes are used in creating cell membrane walls. And when we use the word fat, that usually refers to a triester like you see on the left here. Stearic acid is the nickname for the 18-carbon carboxylic acid. And so tristerin is where that name comes from. So you can see on the left of here we've got what would be 3 stearic acid molecules that would be used if we were creating this ester. And if we are putting all 3 of those in one molecule, that means our alcohol has to be a trialcohol. And glycerol is a very common naturally occurring alcohol. And so our bodies are able to break down fats into the corresponding acid and glycerol, and that's part of metabolic processes that go on in our bodies. Probably the most famous case of esters in the real world are polyesters, the plastics made from esters. And polymers involve fairly simple molecules that are linked to make very, very long chains, and oftentimes the chains involve repeating units that are thousands and thousands of links. So you can see here this thing called terephthalic acid there is a diacid, and so on both the left and right hand side of this molecule you have the opportunity to have an ester reaction take place. And if you react it with a dialcohol like this one, ethylene glycol, you can not only join together 2 of these molecules to make a simple ester, but once you do that, you'd be able to kind of expand on either end of this. So again, like any ester, it involves removing the elements to make water. And on this next slide, it kind of shows that initial ester bond that's highlighted here in pink. And notice that leaves a acid group free on the left and alcohol group free on the right. So if the supply of acid and alcohol continues, this can kind of grow and grow in both directions for a number of units. And this slide shows one diacid terephthalic acid molecule in the middle, ethylene glycols on either side, and so these can go on, these can react at the same time, and in each case producing a water molecule. And it would be very cumbersome to try to draw the entire polyester molecule because it might consist of thousands and thousands of atoms. But here's one way to do it. This is the repeating unit. N here would be maybe a number in the thousands, sometimes in the tens of thousands. And this particular polyester is the one that's used to create, well, all kinds of things. If you look at the bottom of water bottles, it usually has these letters PETE, which stands for that name, polyethylene terephthalate ester. And as it says, this can be Part of the polyester used in clothing. You can make fibers out of this. You can make water bottles. You can make all kinds of objects from this particular plastic. And when that plastic's recycled, it can be depolymerized and reformed and reshaped to create other objects as well. So it's very recyclable as esters go. But it is based on that simple acid-alcohol reaction. And there are some worksheets and exercises from the book to get you practice in naming esters and predicting what their structure will be when they are created.